Hi, my name is Samantha Cox, and my research was on the application of hypochlorite and UV light to the treatment of wastewater. Wastewater can come from storm runoff, industry, or household appliances, and it can contain a lot of bacteria and contaminants that are really dangerous. If they're left in the wastewater, then they get back into your houses and your taps, and so that's obviously they has to be treated to get rid of them. The current processes to do this involve chlorine or ozone radicals that are very reactive and like to attack those organic molecules to break them apart. It's a very effective method, but it's not the most efficient because a lot of times they produce byproducts that are really expensive to get rid of. There's been a lot of research in this field lately involving advanced oxidation processes, which are essentially the same as the chlorine in the ozone treatments, but they use hydroxyl radicals, which don't produce those byproducts. The problem with this, though, is that in large quantities, hydrogen peroxide is pretty expensive also. So there's also been research to suggest that hypochloric acid, which comes from bleach essentially, can be a good substitution for hydrogen peroxide. And you can see in the pictures that the chemical structures are pretty similar. They both have that OH group that can break off, so it's a pretty good substitution. The problem with this one, however, is that it needs UV light to break it apart. It doesn't like to separate on its own. And so when you shine UV light on hypochloric acid at the right wavelength, it actually does break off into the two radicals that you need. The hydroxyl radical is what can attack the organics at that point. For my research specifically, I wanted to look at humic acids in wastewater. These come from degradation of plant matter, so they're everywhere. They're in everything. You can kind of think of them as being in dirt. And in their natural state, they're not harmful at all. I mean, they're everywhere. But when they go through the treatment processes with the chlorine, a lot of times they can produce carcinogenic byproducts, which is obviously, that's very dangerous. So those processes are not the most efficient for this contaminant. The goal of my research was to increase the efficiency of the treatment, so keep or increase the effectiveness while decreasing cost and time and resources. And then those other two values are the national approved values, so I needed to stay within those, or pretty close. This is what my apparatus looks like. So on the left, I have my input beaker, so I put in the water, the bleach, and the contaminants, pump it through the UV lights into the output beaker. It's a pretty simple setup. The variables that I chose to look at were pH, bleach concentration, flow rate, and the number of cycles. So before I could start with humic acid, because I did create my own apparatus, I needed to repeat the experiment with something that's already been done. And so I chose 1,4-dioxane, just trying to get 50%-ish destruction to prove that it is working. You can see in the table kind of how my parameters are summarized. I have 2 to 50 millimolar bleach, 3 different flow rates, and then adjusted or non-adjusted pH. And if you look at the right, really nothing was destroyed of the dioxane until you get to like the two highlighted runs, which are about 40% destruction, which is about 60% remaining. And so I didn't count this as a win because I still went around that 50. But I did say, I have pretty high concentration of bleach, low pH, so what if I run it through the UV light more than once to get more of that treatment? So here's the results when I did that. I used 50 millimolar bleach, so that was like a 1-to-2 ratio of bleach to dioxane, and then a high flow rate, but I cycled it through more than once. And you can see as I cycled it through, it did decrease almost to 50%, which is what I wanted. And so at this point, I decided I had proved the concept and I can move to humic acid. So I basically did 2 runs with humic acid, a 1-to-1 bleach to humic acid ratio, and then a 2-to-1, and then a high flow rate and a low flow rate. You can kind of see these in the table. With the 1-to-1, the top half of the table, you can see that the percent humic acid remaining is really high, almost 100%. And so I decided that that was just super not effective, so I doubled the bleach and lowered the flow rate as much as I could. And with that one, I actually saw about 80% destruction. You can see there's almost 20% left, which is pretty good. And the results are also summarized in this graph. You can see after one run, they decreased significantly to like 100 parts per million, and that's total organic carbon. But after that, it kind of levels off. This is because of available chlorine, and so we're just not reproducing the hypochlorite in solution as much as we could be. And so going forward, I'll be looking at how I can increase the bleach or increase the efficiency of this to meet those national levels. But from this, the research proved that like the methodology is correct and was successful. Thank you.